Today we're looking at Chapter 2. We're starting Chapter 2, specifically looking at the trig functions with acute angles. Very important lecture here, some great insight and some measurements that you need to know. We're going to be looking at using the right triangle-based definitions of the trig functions and broadening those out. We're going to be looking at cofunctions, how function values change as the angle changes, increases or decreases, and then specifically trig function values for special angles. Okay? So we already looked at when we built a graph from a point xy that we knew that we basically had a right triangle with x and y as two of the sides and r as the hypotenuse, and we figured out formulas for each of the 6 trig functions. For example, sine was y over r. Notice that as this is a right triangle, we can make this a more general formula where the sine of an angle is equal to the side opposite the angle over the hypotenuse. Just like we said before, sine A is the value of y over r. So the sine of A here, we could also say, is the side opposite over hypotenuse. And this would hold true for anything. So for example, if we wanted the sine of B is the side opposite, which would be x, over the hypotenuse. Okay? The cosine function translates into adjacent over hypotenuse. So again, for sine A, we're looking for the side next to it over the hypotenuse. For tangent, we're looking for the side opposite the angle over the side adjacent. So the tangent of A is equal to the side opposite, which is y, over the side adjacent, which is x. And then, of course, we have our 3 reciprocal trig functions, which are just, again, the reciprocals of the main 3 functions. For example, sine is the reciprocal of cosecant, cosine is the reciprocal of secant, and tangent is the reciprocal of cotangent. So this leads to a very common acronyms to remember the 3 main functions, and that is SO, CA, TOA. Sine is opposite over hypotenuse, sine S, opposite O, hypotenuse H. So stands for the sine function. So, CA, cosine, TOA, tangent. Sine, opposite over hypotenuse, SOH. Cosine, adjacent over a hypotenuse, CAH, and tangent, opposite over adjacent, TOA. So this gives you a real simple way to memorize those formulas. You know these 3, you know the other 3 because they're reciprocals. So here you have a triangle, and they want you to find the sine, cosine, and tangent values for angles A and B. You might want to hit pause right now and then try this out, put those down on your scratch paper, and then come back. Okay? So the sine of A is the opposite over the hypotenuse, 7 over 25. Cosine of A is adjacent, 24, over the hypotenuse, 25. And tangent is opposite over adjacent, so it should be 7 over 24. Opposite over adjacent. Opposite over adjacent. And then, of course, the other 3 functions. Oh, I'm sorry, we're only doing sine. We're only doing sine, cosine, and tangent. For B, again, the sine is opposite over hypotenuse, 24 over 25. Cosine of B is adjacent, 7 over 25. And tangent of B is opposite, 24 over adjacent, 7. Okay? Went through those pretty fast, but these are pretty straightforward and simple. And these kind of lead us to seeing, if you looked at those measures side by side, A and B, you'd realize that we have some functions which are cofunctions. And specifically, cofunction values of complementary angles are equal. And so what this is saying, if I have the sine of an angle A, that's equal to the cosine of the angle that is complementary to A, or the cosine of 90 minus A. And that's true for sine and cosine are cofunctions. Tangent and cotangent, the same thing. The tangent of an angle A is equal to the cotangent of the complement of A, which you see here is 90 minus A. And secant and cosecant are also cofunctions where their complementary angles have the same trig function values. Okay? So with this in mind, write each function in terms of its cofunction. Okay? So the cosine of 52 is equal to the sine of the angle complementary to 52. So it's equal to the sine of 90 minus 52, or specifically the sine of 38. The tangent of 71 is equal to the cotangent of the angle complementary to 71, which is 19. And secant, the cofunction is cosecant, and the secant of 24 equals the cosecant of the angle complementary to 24, which is 66. Okay. Let's make this a little more difficult. Here we want to find one solution for this equation, and we know that the cosine of theta plus 4 equals the sine of 3 theta plus 2. Well, this is only going to be true if 3 theta plus 2 is complementary to theta plus 4, right? That means these two angles are complementary for this to be true, which means these two angles have to add up to 90 degrees, okay? So if we create a sum that equals 90 degrees, now it's just a simple algebraic problem where we combine like terms, and we get 4 theta plus 6 equals 90, 4 theta equals 84, and therefore dividing both sides by 4, we get theta equals 21. So don't overthink these. It's a little confusing here how to figure this out, but remember that if you have cosine equals sine, if you have the cofunctions being equal, then the angles have to be complementary, or they have to sum to 90 degrees. Okay, same thing here. The angles have to be complementary. They have to sum to 90 degrees. So we add them together. 2 theta minus 18 plus theta plus 18 equals 90. We get 3 theta equals 90 and theta equals 30. Okay? Went through that pretty fast, but you can pause it. You can look at it again. But this is just the idea about cofunctions. The cofunctions are equal for angles that are complementary. So if we have a fixed hypotenuse, if the length of r stays the same, as angle A increases in this diagram, notice that what's going to happen is that side y is going to increase and side x is going to decrease. Now what this means is that because the sine is y over r, the r is staying the same, as y increases, that measure is going to get larger, right? Y over r is the same. As y gets bigger, then this fraction gets larger. So the sign is going to increase. We know that x is going to decrease, and since cosine is x over r staying the same, as x gets smaller, the fraction gets smaller. Okay? I'm sorry, here we went. And because these are reciprocal functions, right? As a fraction gets bigger, its reciprocal, if you flip it upside down, is going to get smaller. So all of the reciprocal trig functions are going to have opposite direction changes. If one increases, as you see here, sine increases, its reciprocal decreases. And that's just the reciprocal of a fraction. A bigger fraction is going to have a smaller reciprocal. Again, cosine A, this is what I was talking about before, cosine being x over r. As x gets smaller, the fraction gets smaller. So the secant is going to increase. Remember that tangent is y over x. So as y increases and x decreases, the numerator increases and the denominator decreases. So this is going to get bigger as well, which of course means the tangent or the reciprocal will get smaller. So, based upon what we just looked at, determine whether each of these statements is true. Is the sine of 21 greater than the sine of 18? Well, remember what we said, as the angle A gets bigger, the sine will get bigger. So this, for part A, this is definitely true. As angle A gets bigger, the sine gets bigger, okay? Remember that secant, which is the reciprocal of cosine gets smaller as the angle gets bigger, so secant gets bigger as the angle gets bigger too. But here we see that the larger angle is less than, so in part B, this is false. Again, for most of what I recommend throughout this trig course is if you understand what's happening with sine, cosine, and tangent, then you can figure out the other three identities. And so that's what I did here with part B. I may not remember what happens as far as secant, cosecant, and cotangent, but I do know as the angle gets bigger for cosine, as the angle gets bigger, the cosine gets smaller, so the cosine is decreasing. It's the opposite of this. And so the secant would have to be a larger angle creates a larger secant. Okay, so to me, this is probably one of the most important parts of this course, and that is identifying the special angle triangles, okay? So I like this build of how you create these triangles. To me, if you understand how to build these specific triangles that we're looking at right now, then you don't have to memorize a lot of values. So first, if we have an equilateral triangle, remember equilateral has all sides the same. So we have an equilateral triangle with sides of 2, 2, and 2. Because it's equilateral, all of the angles are the same. 180 divided by 3 is 60. So all the three angles are 60. Okay? If we cut this triangle in half, notice what we have in 1/2 is, here's a 90 degree, because we're bisecting this. This is a perpendicular. So we have 90, 60, and 30 degrees. Okay? Well, we have a right triangle. We can figure out what this x value will be by using Pythagorean's theorem. Okay, so let's do that. So 1 squared plus x squared is going to equal the hypotenuse squared, or 2 squared. Solving for that, we get that the x side here is going to be the square root of 3. Okay, square root of 3. Now, because of this, this is going to be true for any triangle. We could use this, we could use this triangle to find all 6 functions for 30 degrees or 60 degrees by using SOHCAHTOA, okay? So the sine is opposite. We're looking for sine. We're going to do the 60-degree angle. Opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. Okay? And then we have the 3 reciprocals, which I'm not going to go into. Okay? So knowing this triangle, to me, is much more powerful and easier, at least it is for me. Everyone has their own way of learning and retaining information. But for me, knowing these triangles and actually being able to build them, a lot of times I don't even remember what the side is, but I can remember doing the equilateral 2, 2, 2, and then knowing, okay, we cut this in half, so that's now 1. This side is 2, 30, 60, and we can figure out that with Pythagorean. Then I don't have to remember all of the values around the special angles all the way around the 360-degree circle. So let's look at another triangle. Here we have a 45, 45 right triangle. So we have 90 and then 45, 45. So that means each of these sides is going to be the same. So these sides are 1 and 1. And again, we can now calculate the third side, which is the hypotenuse, by using Pythagorean's theorem. So 1 squared plus 1 squared equals r squared, or r equals the square root of 2. Okay? So now we have another triangle here that we can use to find all of the values. So the sine of 45 is opposite over hypotenuse. Here we've rationalized it. The cosine of 45 is adjacent over hypotenuse. Notice that these are the same measures because these are the same angle, but they're also complementary. Remember, the sine of an angle equals the cosine of the complementary angle. Since these are equal, 45 and 45, and they add up to 90, of course they're going to be the same value. And then, of course, tangent is opposite over adjacent, and this equals 1. All right? Again, I'm not going to go through the reciprocal values. You can look at those yourself. Okay? So a lot of students will commit this to memory, memorizing what happens at 30, 45, and 60 degrees. And this is really important because, again, we're going to look at how these angles appear in the other quadrants, quadrant 2, 3, and 4, etc., and how we can use these measures. But really, again, I recommend you know either how to build these triangles or memorize these two triangles with their measures, because then if you know SOHCAHTOA, sine opposite over hypotenuse, cosine adjacent over hypotenuse, TOA, tangent opposite over adjacent, then you can build, you can figure out these values just by the triangle. And to me, it's a lot easier to memorize two triangles than, again, all of this data. Okay, that's the end of our lecture today. It was a rather short one. Hopefully this has been valuable.